All right. Um,
Okay. Hi, everyone.
okay.
So it's my distinct pleasure to introduce our talker today, Apurva Oza. So he has gotten his bachelor's at the University of North Carolina in Chapel Hill in physics and astronomy, graduated summa cum laude. Got his master's at University of Virginia, again in astronomy, and then got his PhD at the Sorbonne University, pardon my American, in astronomy and astrophysics. He has since worked as a postdoc at the Bern University, University of Bern, sorry, as well as a visiting lecturer at the Indian Institute of Astrophysics and Raman Research Institute, as well as a visiting scientist for the Indian Planetary Society. He's done a lot of work on various moons and planets within our own solar system and has begun working recently on exoplanets as well as exomoons, as indicated by the title. So yeah, really excited to see Oza talk today. And without further ado, if you want to take it away.
All right. Um, One of my monitors just disconnected. So just a real quick fix here. I think you can see everything. All right. Right. So I'm going to talk to you guys today about exomoons, specifically on the origin of evaporating metals at exoplanet systems. And usually I don't put question marks in papers, but I think I'll put a question mark here in the presentation to get thinking on the state of things, the state of astronomy in terms of the next celestial frontier, in the sense that we have now discovered, from galaxies to stars to planets, now to moons. We still need to discover exomoons. As of December 1st, a few days ago, let's see, there were 4,379 confirmed exoplanets, almost the same number of candidate exoplanets, but there are no confirmed exomoons. But there are, let's say, a dozen or so candidate exomoons. And those are the exomoons I'm going to talk to you about today. And I'm going to take this opportunity to also review the field in a general sense, because I think it's been exciting in the last few years, actually. It's picked up. And for all the space science people here, for all the solar system people here, it might be a chance to extrapolate your research to the outside of the solar system world. So hopefully it's interesting. So first, there is this candidate. Let's just go chronologically. I think this is a long time ago. Microlensing candidate. And microlensing technique, for those of you who haven't heard of it, it's when you've got a massive object that passes in front of the starlight, and the starlight bends, and the brightness of the star actually peaks. So usually they use this to detect things like machos here, massive compact halo objects, but you can detect very, very large moons as well. Now, the thing is, for a microlensing event to detect a moon, you won't be able to characterize it. Once you see the signal, it's gone. So you won't be able to confirm the signal. And as you can see from the size of the moon that I put here, it's thousands of moon masses. So you're very sensitive to extremely large objects. Now, next, there is a direct imaging method that has been brought to light, literally. And this is by an Italian colleague, Cecilia Lazzoni. I think she's in Padova, and a very interesting result where they think they see indication of Jupiter-sized moons around a supermassive Jupiter. So they are technically moons. I think they even saw it just based on the orbits, perhaps movement there. But once again, this is tentative and extremely large moons. Moving on to just a little bit smaller, there's Kepler 1625b. This has got a lot of press in the last year by colleague Alex Dici and David Kipping at Columbia. And I just put this in units of moons, not to be crude, but just to see how tremendous the mass has to be and how tremendous the radius has to be for us to detect something in a photometry sense. So this is due to transit timing variation. And the moon that's depicted is blue because it's about Neptune size. So getting a little smaller, roughly 20 Earth masses. I think there's another unit there, but it's very large. Now, something extremely interesting that is also evidence of exomoons, but they're detached exomoons. This is around Tavistarr, also nicknamed the WTF star, for where's the flux. This is, if you look at the left graph right here, people were wondering where the flux was, and they had many, many interpretations of this. Now, you may remember this phone number here, because at some point in time, it was also hypothesized that it was due to an alien megastructure, which I think got lots of press. So recently, Martinez et al., also at Columbia University in New York, they proposed that there are orphaned exomoons, so moons that were normally out at the ice line that got detached and then started orbiting the star. So they're kind of planets now, so not really exomoons, but interesting in that the way they explain it is due to evaporation. And that's the crux of our study. So evaporation is getting us a little closer to how we might find moons that might be smaller than a Jupiter mass moon in the 21st century. Now, here's an interesting study that came from Paris, from Tavistarr and Benjaffe-Lotfi, which people don't really talk about in the exoplanet community because it bridges on these weird asymmetric signatures. So WASP-12b here and HD189733b, very famous exoplanet. We can see that the flux isn't as symmetric. I wish I had a very smooth transit to show you, but you can believe me that they look very smooth, like boxes. Here you can see that there's slight deviation in the very few data points we have here. But even when you model them, they create little dips. So they had proposed this was due to an exomoon plasma torus all the way in 2014. And so here you can see that they did a simulation of the plasma where they're modeling carbon ions and also magnesium ions, which were detected. The catch here is that these moons are outside the Hill sphere of the planet. So personally, I'm always scratching my head on how that works. But it seems that at least they can simulate the light curve and at least the gas is there. Perhaps the moon is captured in the process of being ejected once again, or there's an orbital fixed configuration. But really, that's a segue to our method, because we have now identified dozens of exomoon candidates, which we can sort by temperature, because fundamentally our signatures are due to evaporation. And so we went through microlensing, photometry, and here in 2020, our method is spectroscopy. And that, I think, is the key. And this is what we published in 2019 in the Astrophysical Journal. And it's based on a study all the way back in 2006 from Johnson and Huggins. So also in New York, at New York University. So that is an interesting history there. That this is not really a new idea. It's been around for a while. Okay, so here's a sort of outline, a spectral search for exo-IOs, as we call them. So instead of a photometric survey, so I hope I've demonstrated that those surveys are sort of size sensitive. You really need a big whopping mass to create a dip in the continuum flux of the star or the planet. So the moons are small. So we do something that we call gas sensitive. We want to search for lunar signatures of volcanic volatiles. The issues, of course, are that we must be sensitive to close-in systems, because to use this technique, the planet must transit. And so if it's so close, then there's a possibility that it'll get scattered, that due to dynamics and tides, that the moon will be lost. And so there's lots of work on the formation and loss of exomoons via dynamics, but our work is based on a result in 2009 from Cassidy et al., and where we show that even Earth-mass exomoons can be stable. And today I'm not going to review all the tidal physics, but feel free to ask in the question. And I know some of you have done work on that as well. I think it's an interesting question in, let's say, just dynamics, but it's also interesting that exomoons these days, people, if we have Neptune-sized moons, etc., it's interesting that they can just be captured or just be placed there by any means. But in any case, the moons we're looking for are stable due to the stellar tide. But again, we can review that later. So what we do assume, though, is that they're just formed like giant planets in our solar system. So we think that the Galilean satellites at Jupiter were formed in a circumplanetary disk. So if they're formed like planets around stars, then we would expect that all gas giant planets would have several moons. I think the last time I checked, Jupiter has 79 and Saturn has 82. Now, this analogy is very solar system heavy, and like I said, here's a reference for our stability arguments, just in one reference. If we're making this analogy, a volcanic exomoon would behave like Io and experience similar atmospheric escape and evaporation mechanisms. And that's the physics we want to exploit, and the physics we want to use to detect a small body based on its giant evaporation signature. So you have to compensate for the small body with something else. And here's a little illustration of what I'm talking about. So this is not exactly the scale. As you can see, the exo-Io is much larger, and it should be in from Jupiter. If you've seen any of the nice JUICE videos and simulations, or Europa Clipper ones, you can see Io in the foreground while Europa is coming. Very nice videos. But here I just drew what it might look like at a hot Jupiter. What you're seeing here in orange and yellow is sodium. You can see that the sodium signature expands to the Hill sphere. It fills up the entire Roche lobe gravitational sphere of the gas giant out to several planetary radii, even though the moon is just a fraction of the planetary radii, and it has its own signature. In addition to that, there can be exogenic sources of sodium due to either charge exchange in the plasmators, to evaporating debris, micrometeorites, comets, many things. And also the Roche lobe here can result in shredding of the moon. The tides of the planet, due to the Roche limit for a silicate, can create debris and create a desorbing disk. So there's many sources of sodium, even if the moon isn't volcanically active or just the sole source. It could be multiple moons. So this is just an illustration, and something that I think would be a great PhD project one day, for someone to simulate this in full glory. So maybe I can walk you through the solar system analogy. Here is Jupiter's moon Io. If you haven't had a chance to really ogle at it and bask in its beauty, you can see how yellow and orange it is due to sulfur and many other volcanic compounds that precipitate onto its surface. All these spots here are hot spots due to volcanoes. And I often reference a colleague I have, Carl Schmidt, that some of you may know. Every time he uses a sodium filter and looks at Io, he sees outgassing, he sees a sodium event. It's it's the most geologically active body in the solar system, and there's never a time in history when you won't see evidence of volcanism at Io. It's ongoing, and it's all due to Jupiter's tides. So we want to look at Jupiter's atmosphere due to Io and Jupiter's exosphere due to Io, in hope that this could teach us something about exoplanets or the search for exomoons around exoplanets. So here is Jupiter's sodium exosphere, starting with the biggest scale, 1,000 Jupiter radii. Just for reference, as you know, when an exoplanet transits a star, that'll span only 10 Jupiter radii. So we're talking 2 orders of magnitude larger effect due to just one tiny moon that's a fraction of a Jupiter radii. This is a sodium rectangular, they call it the Mendelosphere after Michael Mendello, who discovered this in 1990. And when you start zooming in, you start seeing the finer details that this is truly just guided by Io. That right here at 70 Jupiter radii and then down to 15 Jupiter radii, that we zoom in and we can see the clouds of sodium that are emanating from Io, and then streams of sodium that are emanating from the plasma torus around Jupiter that contain ions of sodium chloride, which dissociates and creates a sort of transient sodium torus, which is fascinating. So, spoiler alert, at an exoplanet, the radiation is extremely high, and the feature will be shrunk, but that same density and even higher density, column density, would be all contained within a small region around the exoplanet. So we would not have 1,000 Jupiter radii, but a little smaller, but much denser. And looking at Jupiter's atmosphere, so say we have to look at atmosphere scale and transmission spectroscopy. So this was published in our paper. This is also from Oza et al. 2019 B. This was a observation that Emmanuel Lelouch analyzed for us, based on an observation by Enrique Palle's group from Montañez Rodriguez. This is looking at Jupiter as if it was an exoplanet by bouncing the light off of Ganymede. So this is the very complicated geometry one needs to do. It's favorable only because of parallax that be just slightly off, so that we can actually get sunlight to pass through Jupiter's atmosphere and then bounce off Ganymede when it's in eclipse, and then come back to us. And then you subtract each frame when it's in eclipse and out of eclipse. And when you do that, you actually see the sodium doublet that exoplanet astronomers see everywhere. And what's exciting is that we can fit this by just using a very meager column density of roughly 10 to the 11 sodium per centimeter squared, which can either be due to a sprinkle of micrometeorite bombardment or remnant comets. But the most promising is just Io's jets shooting straight into Jupiter, which we know, as we said, like Carl Schmitt's observations, many other people's observations, where you see these sodium jets shooting out of Io that just are totally pervasive in the Jupiter system. So Jupiter's atmosphere is contaminated by an exogenic source, which brings into the question, are hot Jupiters, the exoplanets, are their atmospheres contaminated by exogenic sources, such as hidden exomoons? That's our main question, and you'd only need a small amount is a big point to say, because this technique, as many authors have shown, for example, Le Cavalier des Étangs, 2007, Fortney, 2005, Hang and Kitzman, 2018, the technique is sensitive to tenuous gases, not thick collisional mediums. So we're already sensitive to something like this. although we've been, many interpretations have been thick clouds, or we're running general circulation models to fit. But this technique is inherently sensitive to optical depths around 1. Okay, and here is my favorite GIF or GIF of all time, taken by Nick Schneider, dear colleague who did this over, I think he got very lucky. It says 15 nights, clear nights, where he could take this sequence of images. You can see it jumps a little bit. And if you can guess what is this body coming in, this is a beloved Europa taking the spotlight, but you're just seeing solar reflection off its surface. It has its own sodium exosphere. For example, you can see LeBlanc 2005. But Io's sodium, you can see, is just rotating and is on both sides. There's even spray of sodium here when Io is not there, which is remarkable. So that at an exoplanet, if an exo-Io was transiting behind the planet during the time of observation, which only lasts 3 hours, the orbit could be much longer than that, 15 hours, let's say, then you would still have a chance to see sodium, even if the exomoon is not in front of or even in the line of sight. This is fascinating. And this is because of the plasma torus, which is on the bottom. This is the Io plasma torus, which is gyrating due to Jupiter's magnetic field. There's sulfur ions embedded inside, oxygen ions embedded, and specifically sodium chloride ions that are embedded and trapped into Jupiter's toroidal magnetic field. And you can see it's gyrating on timescales faster than the orbital period, which creates many interesting auroral effects at the icy Galilean satellite. Yeah, this might be a good thing to keep in mind in case the technical details later on escape. So here's some technical details. How to model evaporating metals at an exoplanet. So I have 2 models here, Prometheus and Dkum. The first one being created by Andrea Gebek, who is now a PhD student at the University of Kent in Belgium, and Dkum, which is the model I've sort of been developing for several years now. And both models are quite simple, no fancy, not too many fancy things. So Prometheus, the radiative transfer model with an arbitrary number density input. Here's a schematic of it. And the point here is that we want to offer exoplanet astronomers the chance to test number density profiles that aren't just the barometric law. So n equals n naught exponential minus z over h. We've been fitting exoplanet atmospheres for decades with this, but if an exoplanet is irradiated with a star that's sitting just 10 stellar radii from it, it's possible, very probable, and has been observed that that atmosphere is escaping. So a hydrostatic profile may not be that appropriate. In addition, the volatiles we're looking at, heavy elements, sodium and potassium, is it reasonable to expect they will be just in a hydrostatic fashion in the atmosphere? I strongly contest that interpretation and therefore offer a non-hydrostatic interpretation where you can include different profiles for sodium based on observations in the solar system. Furthermore, the sodium may not be spherical, so we can also test a toroidal atmosphere. And if, let's say, very exomoon skeptical, then you don't need to choose an exomoon into Prometheus. You can just select a endogenic escaping atmosphere, but still you can have a toroidal atmosphere around the gas giant due to, let's say, a magnetic field. So I think this model has been illuminating. This was published in Gebek and Oza 2020 in MinRes. Now, here's Dkum, which is a model that I've developed. I'm proud of the acronym because I didn't cheat. It's desorbing interiors via satellite heating to observe outgassing model. I developed this model to essentially test atmospheric evolution. Here I have it tested for Io. You can see the GIF here. You can see the atmosphere evolving, and then all the lines of sight that are calculated to get the column density, and therefore the spectral signature that's fed into Prometheus. Really, it just takes satellite heating, so something like tidal heating, but it can also take in irradiation from the star, any heat source of a rocky body, and allow it to desorb, build the near surface atmosphere, and then allow that to escape due to various escape mechanisms that we've studied at several bodies, such as Pluto, Europa, sub-Neptune, super-Earths, etc. Okay, so now I just have to move you guys a little bit. Always trying to get on my small screen on Zoom. Okay, so big questions now. How to differentiate between an exoplanet and an exomoon? So by now, maybe you're asking the question, well, this is great. You have your fancy tools to simulate it, but what does it look like, and how do you actually differentiate what an exoplanet is and what an exomoon is? Well, we've thought about this for several years, and I think we have two answers, at least. One is the doublet ratios of sodium and also potassium, and the second is the Doppler broadening. So let's see. The spectral diagnostic of a sodium doublet ratio. So here, SD2 over D1 is if you divide the D2 line divided by the D1 line. So we saw earlier here, this is the D21 line, and this is the D1 line of sodium. So if you divide these two, you should get a certain ratio. If it is near 2, this is indicative of a tenuous medium, optically thin. If it is near 1, it is indicative of optically thick medium. And this is just based off of standard radiative transfer physics, and mainly a result of the oscillator strength of sodium. And the similar result you can get for potassium. And so here is the optical depth plotted in the x-axis, and the y-axis, the ratio. At the same time, the optical depth, just by assuming a certain geometry, you can also recover the column density of sodium. So this is a good opportunity to see how tenuous these columns are. Columns that are barely approaching the line of sight column density at the tenuous vacuums that occur on Jupiter's icy moons. If you just off the top of my head, I know that Jupiter's icy moons, Europa and Ganymede, have columns at 10 to the 15. So obviously this is diluted over the entire star, so it's much smaller. But the point is that high resolution transmission spectroscopy is now finally able to probe such tenuous pressures due to resolving the line core, which we were never able to do for decades, especially when the first observations came out with Hubble. And Hubble Space Telescope remains one of the greatest instruments of all time, I think, for astronomy, but ground-based spectroscopy beats it in terms of resolving these tenuous atmospheric pressures, because low-resolution spectroscopy will broaden the feature and will miss the details, will miss the moons. So that's just one diagnostic. Now, using this D2 to D1 ratio, we modeled two, let's say, ultra-hot Jupiters, WASP 76b and WASP 121b. Their effective temperatures are greater than 2,000 degrees. So if they had pants, they would be burning off right now. Everything is burning, everything is evaporating. The surfaces of any rocky body there would be evaporating. At that point, the question of, is there a volcanically active moon, is moot, because the body is already active by just sitting in a furnace. But when we model them, so these planets, when they're first discovered by exoplanet astronomers, were not interpreted as moons. But it turns out that if you think of a scenario where the moon could be stable and allow for very let's say reasonable parameters of atmospheric escape and orbits due to the hill sphere, and these moons would be very close in, we can actually reproduce these data points. So look at let's just look at WASP 121b. So this is our candidate exomoon. This was published also separately in Hoymakers et al. 2020 in Astronomy and Astrophysics. You can see that the D2 to D1 ratio is roughly 2, indicative of a tenuous medium. If we're looking once again at a gas giant atmosphere, I would expect it to be much thicker, such as WASP 76p, where you can see the ratio is closer to 1. The evaporation rate of the moon to give this is very large, almost a million kilograms a second. So that's 1,000 times higher than at Jupiter's moon Io. But like we said, we're at 2,000 degrees. So not only is volcanism and atmospheric sputtering producing sodium there, there's also straight sublimation from the surface and then thermal energy limited escape, which is interesting. I also like to show this because I did not model in this red dotted line, we did not model the exoplanet atmosphere. This is a toroidal atmosphere produced by a very small, let's say, Enceladus-like exomoon. So a small moon that creates a torus. So it's just evaporating over a large surface area, and we assume that the lifetime is long enough so that due to the magnetic field and recombination, that the moon can actually persist and fuel a torus. So here, this is optically thick. So the diagnostic, even if it's 1, is not indicative of an atmosphere. It could still be a moon. But whereas a diagnostic of 2, here it's very difficult to get such high sodium rates with a ratio of 2. Okay, that might be too detailed. But here's maybe an easier spectral diagnostic, Doppler broadening of atomic sodium. So I say thermal and non-thermal. So on the top, this is from Gebek and Oza, from the MinRAS paper from Andrea. And we can see here that just testing different velocities, a lot of you may know this, but if you just bump the velocity, you will broaden your feature. And what we're finding at these exoplanets, once again, very recently, is that the sodium doublets are broadened tremendously, to the point that a lot of inverse modelers are adding parameters that are arbitrary, in the sense that we can fit it with the exoplanet atmosphere, but the broadening is unexplained. Because as you can see, these are very fast velocities. Let's look at physical processes, once again, analogs at Io. A nominal velocity distribution for sputtering is roughly 30 kilometers a second, 1 to 30 kilometers a second. Now, these are ancient references from Smith et al. And other colleagues you may know of. But charge exchange, pickup ions, you can get to 100 kilometers a second in the Jupiter system, which you can imagine will easily broaden your sodium feature. There's no need to search for an arbitrary parameter where a physical mechanism that is observed in the solar system exists. So we can see here that is a big diagnostic. If you see a broadened sodium feature, that might be indicative of a non-thermal process, which might be indicative of a plasma interaction with the moon. So that's number 2. And here are some inverse modeling that we did as well. That from the data, this is for HD 1897333b, a very bright star, about 5th magnitude. And we can see a beautiful, let's say, constraints in the deviation. We can constrain that the sodium is roughly at 20 kilometers a second here, which corresponds to a certain number of atoms and a certain evaporation rate. So here the evaporation rate is about 10,000 kilograms a second, which is about 2 to 3 orders of magnitude higher than Io at an exo-ion. So what we expect. So even if you do inverse modeling, it tells you that the sodium must be non-thermal. which is interesting. All right, so here is our very first EXO-IO candidate, WASP-49b. Many of you have seen this plot. And let's see, the black points are the data. So you might have to take your glasses off or put your glasses on to see the very small print here. You can see here that the data is broadened, as I was discussing. And we can see that the exoplanet model, the hydrostatic model, cannot reproduce the broadening. It's just far too thin. If we want to talk sigmas, 2 to 3 sigma, too narrow. And on top of that, the hydrostatic, like we discussed, is a crude model, unrealistic. The atmosphere would be cooling due to escape. And so Cubillos et al. 2017 modeled this using their atmospheric escape model. Luca Fossati et al. Also did this, and they get the blue result. And so you can see that the intensity drops even more, narrows even more when you use proper physics. And once again, this is the planetary model. So we used a model from Nick Schneider's group, and also Matthew Berger, who's no longer in the field, but he published very nice sodium profiles at IO. So we had a number density profile, we call it the Berger profile, Berger 2001, indicative of atmospheric sputtering. So we used that and we bumped the mass loss rate by orders of magnitude to correspond to our expected mass loss rate at the moon due to plasma-driven escape, energy-limited escape, Jeans escape, all escapes we calculated. And we found that it fits the data pretty well. And as a modeler, I can tell you that there's very many things, terrible things you can do to fit your model to the data, tweak it, as you guys may know. But really, there wasn't much tweaking here. The sodium is extended to 1.5 RP if we set a moon at roughly 2 planetary radii and let it escape based on the tidal and atmospheric physics we know, and the sodium profile from Berger et al. We actually reproduce this. So to date, I would say this is one of our strongest indications of an exo-IO. And on the right here, furthermore, even if we were missing something for the planet, there's simply not enough sodium shooting from the planet at solar abundance. It would require a very high enriching scenario where I haven't done the exact calculation, but out of thousands of comets that would precipitate onto the gas giant photosphere to give it something like 1,000 kilograms a second. So there's that plot, WASP-49b. And here is a table that I made this morning of all our candidates, just so it's very clear. Did I sort it by anything in particular here? I think I didn't. Maybe it's alphabetical. But anyways, I added a column here, exo rings and torus required. So the real limitation of exomoons, as far as we understand, so of course it may be due to dynamics, they get scattered, migration, but one big limitation is just the evaporation. It's sitting in a furnace. The moon would evaporate perhaps in 100 million years in certain scenarios, especially when you can see Kelt 9b, for example, 4,000 degrees Kelvin. So you can do the calculation for yourself at some point. If you want, you can really do it on pen and paper. These moons would evaporate. So exo rings, torus required, or multiple exomoons. So some of these candidates do require that, which means that an IO-sized moon, if it was baked for 4.5 billion years, or the age of these systems vary, 1 billion years, some of these systems are 10 billion years, it would evaporate, perhaps form a debris disk. And if there is a magnetic field, which we think gas giants do have magnetic fields, these objects would perhaps be trapped in in the form of rings. Now, of course, ions can escape very quickly as well, perhaps grains due to point and Robertson drag, many other phenomena. So it is an open question of discussion. And I think in the end, it does come back to the moon is minuscule in size, perhaps it's captured, perhaps many other avenues, and it's not easy to keep a ring stable. And this is the avenue of our research right now. We have upcoming observations, and so we're using new diagnostics. So a volatile evolution diagnostic, this is in collaboration with Sébastien Charnot at Institut Géophysique de Paris, Globe de Paris, and he's working on evaporating rocks as well, and he's also looking for exomoons. So it turns out we can align this, and so his code, independent of Dkum, can calculate the evaporation of rock based on the assumption that the rocks are a composition similar to Earth. We call this bulk silicate Earth in geophysics, which many of you may know. And what we see here is a sodium to potassium ratio on the y-axis. Let me go do this, is better. Sodium to potassium ratio on the y-axis, and the outgas temperature here. So starting at about 1,000 degrees, the surface simply just starts evaporating. Exoplanets are roughly around here. And we can see in this zone, the sodium to potassium ratio is less than 20. Solar abundance is roughly 16. And so if we get something very small, it's like evidence of just evaporation from the surface. And we can see that it increases very fast with temperature. Of course, the enthalpy and other chemical parameters are not well known, so maybe we wouldn't know these parameters. It's not safe to extrapolate up to higher temperatures here. Of course, this is like if you're just being baked inside the stellar corona itself. Very high, perhaps unrealistic, but I keep this up here because many of you may know that Mercury has a sodium to potassium ratio of 100, and that is also mysterious and very different than the moon, which is down here, only 5 to 6. So you need to have potassium observations to do this. Luckily, there is a new instrument, Espresso, on the Very Large Telescope, built by colleagues at the University of Geneva, which can maybe help us do this diagnostic. And so I did this diagnostic for WASP-52b. And this is a result hot off the stove, which I've been very excited about. This is the sodium doublet here. So you can see at the visible wavelengths. And here's the potassium, one of the doublets. The other one, due to telluric lines, isn't so well constrained. So Chen et al. 2020 actually provided error bars. So I believe observers when they put error bars. And so he put the observation at 6 plus or minus 0.8, which is very, very tight, which means this planet gas giant, this is a gas giant, WASP-52b, maybe roughly between Jupiter and Saturn's size, has a sodium potassium ratio of about 6. This is almost exactly the moon's sodium to potassium ratio. When I do the theoretical calculation with Dkum, I get 4.2, so it's a little higher. But the solar abundance is much higher and does not fit. So in the event that it is a planet, the planet's metallicity would have to be far, far different than solar abundance, from which we think these gas giants are formed. Now, of course, perhaps the star's metallicity, the sodium or its potassium could be different relative to what we have at our own sun. And so those are things to check. Sebastian and I looked the other day. Unfortunately, the stellar observer didn't also provide potassium, but only sodium, which is very, very close to solar abundance, just within a factor of, let's say, if we're talking about plus or minus 0.8, it was plus or minus 0.5. So very close. So we're optimistic here. But yeah, I think, let's see. Moving forward, these are our ongoing campaigns. We have data from 2 of 3 of these instruments right now. espresso. Observations will be taken in, I think, literally a week from now. It was delayed by a month due to COVID. Thankfully, this planet doesn't transit once every year. It transits once every few days and aligns with our line of sight once every month, I'd say, so we're lucky. It's going to be taken from Chile. And we have high-res data that we're collaborating with the Indian Institute of Astrophysics, Athira Uni, who is reducing this data for us, and then Jens Hoymakers at Lund University in Sweden. And a question here, when we're at big aperture telescopes, 10-meter telescopes, 8.2 meter big lunettes, can we see evidence of the dynamics? Can we see the Doppler shifts that are occurring due to these jets? I believe the GIF up, you can see it's moving. Theoretically, if this is the case, and of course it could get jumbled up with the exoplanet atmosphere, other atmospheric escape effects, but we should see some movement. We should be able to get down to what are we seeing in our line of sight. Is this really an exo-IO, or is it complex plasma effects? But at present, there are no complex plasma effects that have been brought up in the literature that are indicative of this. And then the last thing that goes back to the talk, evaporating exo-IOs and evaporating metals, is can we detect more volcanic volatiles? So Jens Hoymakers in Sweden is a very good colleague to collaborate with, because he's responsible for the first detection of atomic iron at an exoplanet, vanadium at an exoplanet, and all these refractory elements. And if you ask me, I would never expect a gas giant to shoot off these elements into the transmission spectra. I would expect it to evaporate, but maybe trace amounts. I wouldn't expect the signature to be so blazing. And the more likely scenario for me is a moon that's evaporating, or you can call it a rock or a third body orbiting a planet or something. But to me, it's just exo-IOs. Yeah, these are our two papers that summarize these results. Encourage you to look at them if you're interested, if you want to get into exomoons, if you like explosions, if you come from gamma ray bursts or something like I did, you might enjoy. Yeah, so I think I'm 4 minutes over time.
All right, thank you, Apurva. The floor is now open for questions. Please raise your hands or just type it out and I'll read it.
I have a question. So at IO, you have geological and volcanic activity driven by not just the gravity of Jupiter, but also the other Galilean satellites, namely Europa and Ganymede. If you have an exo-IO around a Jupiter that's close to its host star, have you looked into how the star might have like a similar effect like Europa and Ganymede do on IO?
That's an excellent question. This is my fault for skipping the results of Cassidy et al. 2009. But what's really nice about that paper is that they derived the influence of the stellar tide, exactly what you're saying, that Jupiter's tide and the tides from Europa and Ganymede, the Laplace resonance, excite Io's eccentricity. So it shows that these exomoons can also be excited, and tidal heating can go into the moon due to these resonances. So it really is due to orbital resonances in a very similar way to the Laplace resonances in Jupiter's system. So in fact, that is how Indicium, when you calculate E dot, the energy dissipation into the satellite, it's based on the results of Cassidy 2009, which includes those effects. So
okay.
it's
Thanks.
yeah.
All right, any other question? Srini, I think you're muted.
Yep, still muted.
Yeah,
Okay.
it's,
I'm just wondering about the time scale on these things, on the
Mhm.
evaporation of exoplanets or exomoons.
Mhm.
What's the time
Mhm.
scale?
Yeah, that's a good question. So let's see. Will you still be able to see this? Can you guys see that paper there?
No, we
You can
see
see this?
I
the-
can
the
see
slide.
we can
the
see
different,
your slides.
yeah, the
Oh, okay, okay.
different
Let me just try to share again. I just want to show you a table
some Malayalam
where we
movie or
calculate.
something.
Yeah, I think this will work. Share. Okay. Oh, there we go. Okay. Here we go. So the time scales. We calculated the evaporation time scales, is what people usually want to know for exomoons and extreme atmospheric escape scenarios. And surprisingly, they can be down to gigayears. So I want to show you the exact table and where to find it. Here's our first candidate exo-IO list. And here, T evaporation, large error bars, but you can see the timescales can be hundreds of gigayears. So,
Okay.
far outlived the star system. But important to say that some of these are borderline scenarios, 12 plus or minus 10. And that's how we flag it as maybe it's a potential ring system. Because if we still see atomic sodium and potassium there, we think there's still something going on there, still suspicious to us, and we flag it. Because if an exomoon was there from the onset, it would have been lost in 100 million years. So those are the sort of timescales we've modeled.
Okay. All right. Yeah. Okay.
Okay, all right. If there are no more questions, then let us thank our speaker, Apurva. Thanks so much.
Yeah. Thank you, Apurva. Yeah. Thanks.
Thank you.
And
Okay.
see you all next week. Bye-bye.
Okay. See you
Alrighty.
guys. Yeah. Okay. Bye.
See you.
Bye, everyone.